Students, in this video we will be looking into Thevenin's theorem, which is one of the most famous theorem in circuit theory. So here is the statement. Any linear active network with the two terminals can be replaced by a single voltage source in series with single impedance. So here is the pictorial representation of Thevenin's theorem. Given a linear active network with the two terminals A and B across which you will be connecting your load, this linear active network can be replaced, or an equivalent circuit for this active network can be found with one voltage source in series with one Thevenin's impedance. In case of DC circuit, this Thevenin's impedance is called as Thevenin's resistance. So there are two steps in finding Thevenin's equivalent circuit for any given circuit. The first step is to find the Thevenin's impedance or Thevenin's resistance in case of DC circuit, and the second step is to find the Thevenin's voltage. So once these two elements are found, then you can put in series VTH with ZTH, and that will be the Thevenin's equivalent circuit for any given circuit. So we will demonstrate the steps involved in finding Thevenin's equivalent circuit by using a circuit like this. In this circuit, let me take this 10 ohms resistance as a load resistance. So RL is 10 ohms, which means that the two terminals A and B are to be considered across this 10 ohms. So now we have got to find out two elements, that is VTH and RTH. So let me find first RTH. The first step in finding RTH is, if load is there in the given circuit, remove the load. Remove the load. And second step is kill or remove all the sources. All the sources from the circuit. Remove all the sources from the circuit. So you have to do these two steps and draw a new circuit for computing the RTH. So voltage sources are removed by short circuiting. This 3 volt will be removed from the circuit by short circuiting, and the current source will be removed from the circuit by open circuiting. So let me show you the circuit. Short circuit of the 3 volts, then 6 ohms. Here you have 6 ohms. And the current source is removed by open circuiting, and I have also removed the load. So this is the circuit which is used for finding the RTH. Now please look into the entire circuit from point of view from AB. So what is the equivalent resistance across AB? So if you look from A, you can see that if I travel here, the two resistances 6 ohms are in parallel. So the resistance across AB, the other name for resistance across AB is Thevenin's resistance, is nothing but 6 in parallel with 6, which is nothing but 6 into 6 by 6 plus 6, 36 by 12, which is equal to 3 ohms. The next step is to find the Thevenin's voltage. The other name of Thevenin's voltage is open circuit voltage. So the first step that you have got to do to find VTH is remove load if it is given. Second step is find voltage across the open circuited terminals. So now the circuit will be, so sources are to be present. You should not remove the sources are to be present in the circuit. Only thing is you will open circuit or you will remove the load. So 6 ohms, 3 volt, 0.25 amps, and I have removed the load. Exactly, I should say that I have open circuited the terminals AB. So using this circuit, now we have got to find out what is the voltage across this A, B terminals. You can use any method which is convenient to you to find this voltage across AB. So now I think for me it will be easy if I convert this current source into voltage source. 6 ohms. Here there is a current source and there is a parallel resistance, isn't it? So this one I am going to change it into a voltage source in series with 6 ohms. So I can do like this. AB 6 ohms in series with this voltage source is V is equal to I into R, 0.25 into 6 ohms. You will get it as 1.5, isn't it? 1.5 volt. Now voltage across these 2 points, if you find, that will be the voltage across AB. So let me use Kirchhoff's voltage law to do this. Only one in this circuit, there is only one loop starting from 3 volts, 6 ohms, 6 ohms and 1.5 volt. Let me assume a mesh current I and apply KVL to write the mesh equation. So minus 3, according to the loop current direction, the polarities are like this, isn't it? So plus 6i. We have already dealt in the previous videos how to write a mesh equation, how to apply KVL to a closed loop, and all those things we have discussed in the previous video itself. So here 6 ohm again, so 6 into I plus 1.5, sum of all voltages is equal to 0. So I is equal to 1.5 divided by 12, that is equal to 0.125 amps. So the voltage across these 2 points is found by this 6 into I, that is the potential across the 6 ohms, isn't it? 6 into I is 6 into 0.125. 6 into 0.125 makes to 0.75 volt. So see the polarities from this point top to bottom. When I cross, the polarities are plus minus plus minus. So the voltage across AB is nothing but 6 into 0.125, which is 0.75 volt plus 1.5. So it is 2.25 volt. VTH or VAB is 2.25 volt. This voltage VAB is called as open circuited voltage because I am finding voltage across open circuited terminals. So first initially I open circuited this terminal by removing the load, and I am finding the voltage across these two terminals. So it is also called as open circuit voltage, VOC. The other name is Thevenin's voltage, or students can give a name like VAB. So now the Thevenin's equivalent circuit. Thevenin's equivalent circuit. So VTH is 2.25 in series with 3 ohms. RTH is 3 ohms. This is 2.25 volt. And now you can bring in the load. So initially the load was removed for in both cases, in RTH case as well as in a VOC case. Now the removed load can be brought in 10 ohms. So this is my Thevenin's equivalent circuit. So if you would like to find what is the current through this load, then this is a single loop. So the current through the load resistor, that is current through 10 ohms, can be found by 2.25 divided by 10 plus 3, that is 13 ohms, which you will get it as 0.17 amps. So even if you want to find the power across 10 ohms, you can use I square R, that is 0.17 square into R. That will give you the power dissipated across this resistance, load resistance 10 ohms. So students, let us discuss the Norton's theorem in the next video.